Hello everyone, my name is Harvinder Khera and today I'll be giving a short demonstration on quantification of DNA and proteins by UV spectrometry. So the quantification of DNA, RNA and proteins is regularly done in all the molecular biology labs. There are different methods for estimation of the quantity of these biomolecules, but UV spectrometry remains the method of choice because of its ease, quickness and less sample requirement. We are able to use this method for quantification of our biomolecules because the building blocks of these biomolecules are able to absorb the UV light. In case of DNA, the heterocyclic bases are aromatic and they absorb in the UV region of electromagnetic spectrum. It is noteworthy that the lambda max of all the Watson and Crick bases is between 250 nanometers and 280 nanometers, making it possible for us to use this method for quantification of DNA. As you can see on the right hand side, there is a typical absorption spectrum for DNA, RNA and proteins. You can clearly see that the absorption of DNA and RNA have peak about 280-60 nanometers, whereas the proteins have the peak absorption at about 280 nanometers. For proteins, it's mainly the aromatic amino acids like tryptophan, tyrosine, phenylalanine and the disulfide linkages that constitute the chromophores and absorb the near UV region. Absorption of near UV radiation by proteins is usually monitored as set at 280 nanometer due to the high absorption of tryptophan and tyrosine at this wavelength. So the principle of quantification of these biomolecules lies in the Beer's law, which states that the absorption is directly proportional to the path length and the analyte concentration. So if we know the absorbance, path length, and the molar absorption coefficient, we can easily calculate the concentration of our analyte. So the question is how to get the molar extinction coefficient. For quantification of nucleic acids, there's a simple relationship for the molar extinction coefficient, which is given over here. For double stranded DNA, it is 0.2 micrograms per ml per centimeter. Similarly, for single stranded DNA and RNA, we know the molecular extinction coefficients. Similarly, it is very straightforward to calculate the molar absorption coefficient of your folded protein if you know the sequence of your protein. As already mentioned, it depends on the number of tryptophan and tyrosine molecules as well as the disulfide linkages in your protein. Once you have the information, then you can easily calculate the concentration of your DNA, RNA or protein. Moreover, it is really important to calculate the purity of your sample, as different contaminants like phenols and salts which we use during the extraction of our sample may still remain in the sample and may interfere with the true values and skew your results. For a pure DNA, the ratio of 260 to 280 should be around 1.8. For RNA, it should be around 2, and for pure protein, it should be around 0.57. Here is a short video showing quantification of DNA using Ticken instrument available in our lab. So with the present technology, it is pretty straightforward these days to do such experiments. All you require is 1 microliter of the DNA. As you can see, I have loaded 1 microliter of my sample on the plate provided with the instrument, and I'm loading the plate onto the instrument, and now I'm giving a command to the instrument so that it can take the absorption. So with single command, I'll be able to get the concentration of my sample. It'll take just a minute to get the results. As you can see, the instrument is measuring the absorption, and now it has given me an Excel sheet which shows the 260 280 absorption as well as the ratio, and shows me the purity of my sample as well as the concentration of my sample. So the concentration is 79.8 nanograms in case of my sample, and the ratio is around 1.68, which is kind of okay. So this is how we calculate the quantity of our sample, which could be DNA or protein, using the instruments available. Thank you very much.